In the previous lectures, like we covered vector spaces. There, I mentioned as an example of a set of n cross n real matrices or the field of reals to be a vector space, or a set of m cross n matrices or a field of reals to be a vector space, or a set of polynomials of degree n with real coefficients over a field of reals to be a vector space. Okay, so as we proceed further, I'll explain you how these elements like the m cross n matrix or a n cross n matrix or a polynomial of degree n, or why are these called as a vector. Okay, because if you remember the definition of vector space, we said a set of elements also called as vectors. Okay, for the definition of vector space. So why we call it as vector? What you would be as of now familiar with are vectors basically that are drawn in on a plane, or what we refer to here as the R2 space. So you define a x and a y axis, and in this x or y axis with this as the origin, you would say that this is a vector. So the vector would have some length and an angle, or other there is some coordinate with respect to x-axis and some coordinate value with respect to the y-axis. Okay. Similarly, for a three-dimensional case where you say that you have three orthonormal axes x, y, z with this point as the origin, you would probably say that this is a vector which is of the form ABC, where A, B, and C are coordinates with respect to the x, y, and z axis that you have drawn. Okay, so from here you would have always seen vectors to be of the form x1, x2 till xn if it is a n tuple vector, right? This is a n tuple vector, and how would you have represented this? You would have represented this as xi belongs to R. Okay. So you have vectors in R2, R3. You would have probably seen or talked of vectors in R4 when you talk of hyperspace or hyperplanes. You would have talked of Rn and so on. Okay. Now, as we proceed further, we'll see that if there is a vector space, basically m cross n, uh, or rather a set of m cross n real matrices with field being reals. When you call this as a vector space, let for simplicity let m be equal to 2 and n also be equal to 2. Okay, so the vector v belonging to the set this calligraphic v, for example, let's say 1, 2, 3, 4. Why am I calling this as a vector? Can I represent this in a similar way to which you are already familiar? Okay, because if I can represent this, you would be convinced that, or I can rather convince you that this is actually going to be a vector. Similarly, if my vector space is a set of polynomials of degree n and the field is uh, reals, and let's take a vector from this set such that, again, for this I'll choose my n to be equal to 2 for this example. I can write it as So why can this be, or how can this be represented in terms of vectors? Okay, we will see that as we proceed further. In this lecture, we will be discussing of something known as linear independence. So, to understand linear independence, consider this. Consider that there are two vectors, okay, and this is the R3 space, okay, and these are two vectors. Let us label them as vector 1 and vector 2. Let us introduce another vector as well. Consider it to be vector 3. Okay. So you have a set of three vectors v1, v2, and v3. Okay. So now the question is, can I express v1 in terms of v2 or v3 or both? Okay. Similarly, can I express v2 in terms of v1 or v3 or both? And same for v3. Okay. So if one of these vectors, okay, can be expressed in terms of the other vectors in this set, okay, then we say that the vector is dependent on the other vectors. Okay, so if I can express v1 in terms of v2 and v3, where alpha beta belong to the field, okay, then I would say that v1 is dependent on v2 and v3. It might so happen that in certain cases, okay, in certain cases v1 cannot be expressed in terms of only v3, or v1 cannot be expressed in terms of only v2, and it requires possibly both the vectors to be finally obtaining v1. Similarly, in certain cases, depending on the choice of v1, v2, v3, v1 can be expressed only in terms of v2, or v1 can be expressed only in terms of v3. Both of them might not be. So either this is true or this is true. Okay. Now, if it so turns out that the given set of vectors is such that v1, v2, and v3 cannot be expressed in terms of each other, okay, then these three vectors are linearly independent. Please note that when we talk of linear independence of a set of vectors, we are assuming that all the vectors in the set are non-zero vectors. So I should say that v1 not equal to 0, v2 not equal to 0, and v3 not equal to 0. All the three vectors that we are considering here are not. Then for linear independence, the set of vectors that we consider are always non-zero vectors. So if v1, v2, v3 cannot be expressed in terms of each other, then they comprise of a set of linearly independent vectors. Now, why does that term linear come in? And now, if you notice the relationships that I have written here or here or here to express v1 in terms of v2 or v3, they're all linear with respect to the vectors. Okay, so the expression of v1 as alpha v2 plus beta v3 is linear with respect to the vectors v2 and v3. Similarly, v1 equal to alpha v2 or v1 equal to beta v3, they are also linear relationships with respect to v2 and v3 respectively. Okay. So they cannot be expressed linearly with respect to the other vectors in the set. Okay. So now how can this be formally put down? So we can say that a finite set consider a vector space V over a field F. A finite set of vectors Vi belonging to this for I equal to 1 to L. L is some finite positive integer, and so this set represented by what I should say is this symbol. Okay. A finite set of vectors represented by this, such that all vectors are non-zero vectors. A finite set of vectors represented by Vi such that all vectors are non-zero vectors is called, we first define what is linear dependent, is called linearly dependent set if there exists a corresponding set of scalars. Okay, corresponding set of scalars represented by alpha I. And what are the scalars going to come from? They are going to come from the field. Not all zeros. So we have a set of scalars where not all of the scalars are zero, such that if you take a sum of the scaled versions of the vectors, then the sum turns out to be a zero vector. Okay. So For example, in the above case where we had considered a set of three vectors, what we said was v1 is alpha v2 plus beta v3. Of course, alpha and beta, at least one of them is not zero. This is essentially nothing but v1 minus alpha v2 minus beta v3 to be equal to 0. So I can write this as sum of I equal to 1 to 3 alpha I vi to be equal to 0, where alpha 1 is 1, alpha 2 is alpha, no, alpha 2 is minus alpha, and alpha 3 is minus beta. Okay, so this is possibly a set of scalars where not all of them are zeros, yet the sum that we have taken as alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 turns out to be 0. Okay, basically this statement here indicates that one of the vectors can actually be expressed as a linear combination of other vectors. Okay, so to put it in another way, if alpha v1 plus beta v2 plus gamma v3 is equal to 0 for, let's say that all the scalars present are not 0 in this particular case, in this example, and this essentially would mean that I can write this as v1 is equal to minus alpha inverse beta v2 minus alpha inverse gamma v3, which are nothing but some scalars beta dash plus and gamma dash. Minus alpha inverse beta is beta dash and minus alpha inverse gamma is gamma dash, which essentially means v1 can be expressed in terms of v2 and v3. So what does linear independence mean? If the set of vectors is not linearly dependent, then it is linearly independent. So to put it mathematically, this means that suppose you take a linear combination of the vectors, you take a sum of the scaled versions of the vector, and you try to find out the values of these scalars so that this sum turns out to be 0, and it so happens that alpha I is 0 for all I and the non-zero vi's that you have taken in the set. If this happens, then what does it mean? It means that none of the vector can be expressed as a linear combination of other vectors, okay, or can be expressed as linearly with other vectors in terms of other vectors. So then we can say that the set vi of non-zero vectors is linearly independent. Please understand what is this saying. Suppose you form a equation with the given set of vectors. And what is that equation that we are going to form? What you do is scale up each vector by a factor alpha I, and then add up the scaled versions and equate it to 0. Now if you solve this equation, and it so turns out that this equation is only possible, or the only solution to this equation is such that all the alpha i's are 0. Okay, is possible if and only if all the alpha i's are 0. So I'll write it this way. The solution to the equation of the sum of scaled up vectors is that the scaling factors, all the scaling factors are 0, implies that the set of vectors that you have seen, when I say set of vectors, by default I am assuming that it is a set of non-zero vectors. So the set of vectors that you have is linearly independent. None of the vectors in the set, you pick up any vector from the set, it can never be expressed as a expressed in linear terms of the remaining vectors, what we essentially would be calling as linear combination. We'll see it in the forthcoming lecture. The reverse implication also holds. So if you already know that a set of vectors, non-zero vectors, is linearly independent, then it is guaranteed that if you take a sum of, if you take a sum of, or sum of the scaled versions of the vectors, and you want the sum of the scaled versions of the vector to be 0, then this is only possible if the scaling factors are 0. So the reverse implication holds. So this is a if and only if statement. How we can see this is that a set of non-zero vectors vi is linearly independent if and only if the solution to the equation summation alpha I bi equal to 0 is that all the scalars associated are 0. Okay, so let us see some examples. Consider the set so this set is a subset of the vector space R3, and I am considering the field to be real. Can you let me know if these two vectors are linearly independent, or are these two vectors linearly dependent? So what you do is take two scalars, treat them as unknown scalars, but the scalars belong to the field that we have considered. Use those corresponding scalars to scale up the vectors. So I am using alpha to scale up the vector 1, 2, 3, and beta to scale up the vector 4, 5, 6, and equate it to the 0 vector. So from here, what we get is a set of equations. What are those set? You get alpha plus 4 beta to be equal to 0, 2 alpha plus 5 beta to be equal to 0, 3 alpha plus 6 beta to be equal to 0. Now given this system of equations, what are the values of alpha and beta so that the scaled up versions, corresponding scaled up versions of 1, 2, 3, and 4, 5, 6 when added up give you a 0. One can easily verify that the solution that ensures this is alpha equal to 0 and beta equal to 0. Of course, if you set alpha equal to 0, beta equal to 0, these equations hold, but it so turns out that the only solution that this equation has is alpha equal to 0 and beta equal to 0. Now, because this is true, let us represent this set as some capital X. So the given set of vectors is linearly independent. Similarly, consider another set. We'll consider the same set of vectors 1, 2, 3, 4, 5, 6. With it, we'll take one more vector in the set. Again, so this is a different set. This set has 3 vectors, all vectors are non-zero. I am considering the field to be reals, and we have to check whether this set is linearly independent or not. Take up 3 scalars, unknown scalars from the field. Three unknown scalars, let us label them as alpha, beta, gamma. They belong to the field, this field of reals. So I have alpha 1, 2, 3 plus beta 4, 5, 6 plus gamma 7, 8, 9 to be equal to 0. Right. Now, what are the solutions of alpha, beta, gamma so that the sum of these corresponding scale versions will turn out to be 0? Of course, once one solution is you set this to be 0. The question is this the only solution? And the answer is no. One possible solution that you can think of so that the sum of scaled vectors is 0 is you set alpha to be equal to -1, beta to be equal to 2, and gamma equal to 1. This solution can also imply that the sum is 0. Now the question is this the only non-zero solution? Please note that since we are able to find at least one set of scalars where not all scalars are 0, the given set of vectors is not linearly independent. So we'll say that the given set of vectors is linearly dependent. Okay. X is a set of vectors which is linearly dependent. Okay. Now, to examine further, is this the only non-zero solution that you have? And again, the answer is no. You take, if you set alpha to be equal to minus gamma, so let's say that you fix a value of gamma, fix gamma, take some value of gamma, choose a value of gamma. And if you take alpha such that it is equal to minus gamma and beta so that it is twice the value of gamma, then this set of scalars will always result in the zero vector when we take the scaled up versions of the corresponding vectors and add them. You can see here that if a set of vectors is linearly independent, then the solution to the equation is one and only one, which is all the scalars are zero. I'll write it down. If a set of, let's say, a finite set of non-zero vectors a finite set of non-zero vectors is linearly independent if and only if alpha I vi equal to 0 has alpha equal to 0 for all I as the only solution. Okay. If a finite set of non-zero vectors is linearly dependent, then has multiple solutions. Of course, 0, 0, 0, all scalars being set as 0 is also a solution, but apart from that, you have other solutions as well, and possibly and actually infinite solutions. Okay. So, in during this lecture, you would have heard me using the term linear combination. We'll see what this linear combination is in the forthcoming lecture. Thank you.